Hey, what's up, guys? Welcome to another episode of the Modern Goonies podcast. I'm your host, Trevor King Minor, hanging out with my badass co-host, Michael Ross.
It's your fucking boy, Michael Ross.
So, welcome to Season 1, Episode 9, and today's topic is Neutron Stars. So, we're going to go through and discuss one of the most fascinating and strange galactic structures in the entire universe. And this is right up Michael's alley because this just actually happens to be an area of his concentration within his master's degree in physics. So he's got a lot of in-depth knowledge on the topic, and I'm just going to kind of discuss my basic understanding, asking some questions along the way, and he can correct me in all of the false facts that I spout off. But yeah, so I guess for starters, I asked you this personally the other day, but why don't you kind of explain a little bit like your background with neutron stars, because you know a lot more than I know any of our friends do. So,
well, what sort of questions? What sort of background? Like I could go into my research, but it's a little too complicated for the
maybe give a general
podcast.
Maybe give like a general overview of what your research is. Like, don't go in too much depth. Kind of talk maybe a little bit about like what your thesis is, and then also I would like to know how you got so interested in it that you're like, I want to study that specific area for my thesis. So,
okay, so my research has to do with finding information on nuclear matter.
Okay.
Nuclear matter is basically just matter made entirely of protons and neutrons. Like nothing like what we'd see on Earth.
Yeah.
There is either an equation or a set of equations that describes how nuclear matter behaves under certain conditions. And that the equation or set of equations would basically give you how nuclear matter would behave under every condition in the universe, from low density to high density.
Okay.
So there are certain, I feel like I've got to go into background. So basically I'm looking for that equation.
Okay.
And I'm using real data to kind of poke at that equation.
Okay. All right, interesting. Okay, so how did you kind of get into this field? Because I know, physics is like a pretty broad thing. So how did you kind of like concentrated into that area? What about it fascinated you, I guess?
Well, space is always interested me. Like since I was in third grade, I remember reading a space book. So if I didn't do research on neutron stars, like it would have either been black holes, how stars evolve, or like something space related. I just happened to approach my current advisor first, and his research is on neutron stars. So the first project he gave me was neutron star related, and I was like, holy shit, this is cool.
Yeah, they are pretty fascinating. And like one of the things I didn't realize about it until I started kind of looking into it a little bit is that they're actually one of the strangest fucking things in the entire universe. They're very unique. They're very weird. Like a lot of their physics is pretty wonky. Like I don't know. It's pretty crazy. So I know when you went to tech, you were going to be studying geology.
Yep.
So how did you make that transition from geology into physics? What was the thing that made you kind of shift over?
Well, the major point was Texas A&M Commerce didn't have a geology program.
Okay,
and so I waffled from degree program to degree program for the first semester, trying to figure out what I liked. And while I was in one of my math classes, what happened was I was a industrial engineering major.
Oh, I didn't know that. Shit, yeah. That's cool. All right.
At one point, I had a major in industrial engineering, and I had to take a physics course as part of that major. So the very first day of my physics course, I was like, damn, this is kind of cool.
Yeah.
And so later that semester, one of the students said, hey, you should change your major to physics. And I was like, okay, what's physics about? And so she told me what physics was about. And I thought, okay, that sounds hard, but cool. And so I changed my major to physics.
That's all it took to change your major? Holy shit, bro.
That's all it took.
If someone was like, hey, you should change your major to this, I'd be like, LOL. It'd be one of those things I'd be like, yeah, maybe. And then I never look into. But that's pretty cool that all you needed was a suggestion and be like, describe it. It's this. All right, I'm changing my major.
Yeah.
Nah, that's pretty cool. Okay, yeah. So I'd say like let's go into it. So I did a little bit of research, once again through Kyrgyzstan, PBS Spacetime, just kind of like the general lay person's stuff.
Yeah.
So before we kind of discuss some of like the really cool facts about neutron stars, because there's a lot of cool like trivia that's just kind of blows your mind about them. I think we should kind of discuss like what they are, but instead of trying to be like, oh, it's this star that whatever. It's like I think maybe we should maybe go into kind of how they're formed a little bit first. And so that way people kind of get an idea of like, oh, okay, it's a star that comes about through XYZ process.
Okay.
So I have like a general overview of things. I'm going to kind of go through it. And if I go along and I say something that's a little inaccurate, you can go ahead and be like, well, you can correct me and whatnot. But okay. So, basically like within just like a regular star, there's about, like the mass of trillions upon trillions of plasma are all kind of being pulled towards its center, like through gravity. And so when the force is so strong that it kind of like squeezes material where they start to bond within the star. So hydrogen is formed within, and it then kind of fuses into helium, if I'm not mistaken. Like there's helium within a star.
Yeah.
Yeah. Okay. So then the helium it pushes against the gravity of the star, and it pretty much tries to escape, but it's kind of kept compacted within due to all the gravity that's weighing it down. More or less?
More or less.
Okay.
Like through nuclear fusion, pressure is produced.
Okay, yeah.
So when hydrogen fuses into helium and helium eventually fuses into something else, pressure is produced to balance gravity. That's why stars remain in equilibrium.
Yes. Yeah, and that's pretty much like a lot of what I'm seeing is like, the transformations that stars go through is basically like one equilibrium being thrown off in one way or another.
Yes, exactly.
And that's pretty much, so yeah, stars literally is just like this balancing act of chemicals, fusion, pressure, like all of this crazy shit within. So pretty much as long as that balance remains, stars kind of remain in a stable state, like as we know them, as our star. Right? The balance is pretty good. It's just a regular star. It's not going to fucking blow up and kill us. Like everything's totally fine. So at a certain point, all of the hydrogen becomes exhausted and the star kind of starts to enter its phase of death, is from what I understand. So for stars about the size of our sun, that means that at a certain point it's going to expand kind of as it burns through its helium, and it becomes a supergiant or just a giant. That's where it becomes a red giant. It encompasses like all of our Earth and like the 4 innermost planets, and it fucking kills us all. And then eventually it becomes a white dwarf. And so that's for stars about our own size. But I don't actually know like what a white dwarf is. Can maybe you explain it like a little bit? Because that was one of the things that I was like, all right, like I saw that. I have like a basic idea, but I was like, I'm not going to go into any research. You can probably explain it better than I could.
So a white dwarf and a neutron star are actually very similar in that regard, in that they're both cores of stars. A white dwarf is the core of a smaller star after the outer layers of the star have been stripped away.
Oh, okay. That's pretty cool. Yeah, okay, yeah. So I wanted a little bit of clarification on that. I mean, that was pretty simple. I probably would have watched a long-ass video of it trying to explain it to me, and I'm still confused at the end. Okay, so that's what happens with a star about our size. So,
the size of the sun.
Yeah, about the size of the sun. So, but for stars that are much larger than our own star, the process is a little bit different. So, once these stars, and we're talking like stars that are fucking way bigger, like they're massive-ass stars. So once their helium is kind of exhausted, the balance between pressure and radiation tip in the favor of gravity, which pretty much overtakes the star. So it starts squeezing the star towards the center with much more force than before. So from there, the core burns hotter and faster, while the outer layers they swell and they fuse heavier and heavier elements within. And it keeps fusing these elements until it pretty much hits like a metaphorical bedrock, which is iron, and nothing else can fuse after that point. Which that always kind of blows my mind, the fact that there's like iron within a star. I don't know. It's just always like pretty crazy.
Yeah. So the reason that happens is because iron is the first element where fusing it iron in the periodic table is the first element that takes more energy to fuse than you get out. So by fusing iron, the star effectively runs out of energy. It can't counterbalance gravity anymore with pressure.
And that's pretty much exactly what I read. And so from here, there's no longer any more outward moving pressure. So the balance is thrown off. And now the iron core starts to become crushed from the weight of the star surrounding it. So this is pretty much where the star starts to implode, and the pressure within is so great that electrons and protons fuse to form neutrons, and all of these neutrons kind of start getting jammed compactly into one space with one another. And so the iron core at this point is about the size of the Earth, so that's about the size of the core of this gigantic star, and it's condensed from the size of our Earth into only nuclear material that's about the size of a city. It like crushes it all down from Earth size to about the size of a city. And it's so from there, the outer layers of the star start to implode towards the core at about 25% the speed of light. So the outer layers of the star bounce towards the core, going ridiculous speeds, and it pretty much bounces off of the core, and it causes a galactic explosion, which we know is a supernova. And it's so bright at this point that it outshines entire galaxies. So what remains after this explosion is a neutron star, which now has the mass of about 1 million times the mass of the Earth, and it's all compressed into a space about the size of 16 miles wide.
It could fit inside Dallas or Vancouver.
Yeah, it's insane. So here's where I have like a question for you. So isn't this like basically the same process that occurs like when a black hole is formed? Like this essentially, from our reading and my research on black holes, like this is pretty similar.
Yeah, like exact same thing.
Yeah, and so my question is like, what's the difference? So what's like the boundary between a star is going to become a black hole or it's going to turn into a neutron star?
The boundary is the mass of the initial star. If the star is greater than 25 times the mass of our sun, then, I mean, roughly, these are rough estimates. If it's roughly 25 times the size of our sun or greater, it's going to become a black hole. If it's between 10 and 25 times the mass of our sun, it's going to be a neutron star. And less than 10, it's going to be a white dwarf. Okay,
that's it. I didn't know that. That's interesting. Yeah. So then I guess from here we could probably go into like some facts. So do you have any? I have like a few cool things that I wanted to say about neutron stars. But like, what's one of your like first things that you would like people to know about them? That's like pretty dope. You can start going on. This is where you can start going on your tangent about stuff.
Okay, cool. So the first thing that I think nobody really knows about neutron stars, like it's just starting to make its way into like popular science, but neutron stars have exotic phases of matter called nuclear pasta.
I wanted to talk about this. This is a bullet point I have on here. I thought this was so cool. Anyways, go ahead.
Okay, so nuclear pasta is actually something that I did research on. Just a little bit. Before we talk about nuclear pasta, I guess we should talk about the structure of a neutron star.
Okay.
So a neutron star is much more planet-like than star-like. Like it's basically analogous to the Earth in that it has a crust, a mantle, and a core. Just like our planet does.
Yeah, and I read that that some of them actually have like a very basic form of their own atmosphere as well.
Yeah,
and that I thought that was really cool. I didn't realize that it could have kind of like a planetary structure to it. I thought that was really dope.
Yeah, and that's not. I think that's something that a lot of people don't realize. But I mentioned the structure of the neutron star, how it's like the Earth. So in the crust / mantle, they call it the crust core transition. In the time between the crust and the core, there's a boundary where nuclear pasta begins to form.
Yes.
And nuclear pasta is basically nuclear matter, which is just protons and neutrons subject to very high densities that take the shape of pasta, basically. Like
it basically like starts to kind of like string it out, and like the way it stacks it and compacts it together, it basically makes kind of the shape of lasagna.
Yes. So if you were to take a, say, 1 foot by 1 foot, nuclear pasta is more microscopic. So let's pretend we took a 1 foot by 1 foot thing and we blew it up like 100,000 times.
Okay.
Then you would see microscopic like sheets of quote unquote lasagna looking structures.
Yeah.
And the shape of the nuclear pasta changes depending on how far into the star you go, because its shape changes based on density. The further into the star you go, the more dense it is. Yeah. I mean, that seems kind of basic. It's the same thing as the Earth.
Yeah.
So nuclear pasta comes in I think from lowest density to highest, you have gnocchi shapes or spherical, quote unquote, pasta type deals. Then you have spaghetti, tubes of nuclear matter. Then you have the lasagna. And then you have waffle shaped, quote unquote, spaghetti type deals.
Scientists are weird people.
Yes. And then as the density increases further, you get anti-shapes. Like imagine having a box with a sphere cut out. That would be the anti-gnocchi.
Okay.
Or imagine having a box with a noodle shape cut out.
Okay.
That's the anti-spaghetti.
Interesting.
Yeah.
Yeah, this stuff is really weird. So like I read that this stuff could basically be the hardest material in the entire known universe. Like unbreakable in almost every sense. Like it is the Minecraft's bedrock. Like you cannot get through this shit.
Yes. Like according to what we have, or according to the knowledge that we have, nuclear pasta is the strongest material in the universe.
That's so fucking cool. Yeah, and so I started reading a little bit about that, and then something else I thought was like cool, and you probably know more about this, but when you kind of start getting into the core of a neutron star, they don't actually know kind of the reactions that go on within this core, because like it is so neutron stars are so dense that they're basically like a couple steps below a black hole. Like they are one of the densest and most, like, their gravity is so strong they're basically equivalent to black holes. And so like when you get within the core, it's so unbelievably dense they don't even know, like physics just start looking like super wonky. So like can you describe that a little bit? I don't know if you've done too much research into like what the reactions within the core.
So I can only tell a little bit because my research didn't actually concern the core. It specifically concerned the crust.
Oh, okay.
But what I do know is that inside, this is also impossible to test, impossible to prove.
Right, yeah.
But what we know about physics says that the inside of a neutron star, among other things, could be just a gigantic soup of quarks and gluons.
Yeah, I read that as well.
For those of you who don't know, quarks and gluons are what make up protons and neutrons. So protons and neutrons form the basis to everything around us, but even smaller than protons and neutrons are quarks and gluons.
Yeah.
And I mean, basically, there could just be a sea of quarks and gluons inside of a neutron star, and we'll never know.
Yeah. Yeah, so it's that, and then I also heard a little bit about, and I didn't end up watching the video over what was called like strange stars, but they also believe that, like, you know, maybe the way that they actually do end up fusing, and instead of being quarks and gluons, it basically creates what's known as like strange matter, which is, I didn't go in depth on that at all. I don't even know what that means, but pretty much just something super wonky that's hard to describe, that only if you push physics to the absolute brink, it would create something really fucking weird within. But
so I don't know very much about strange matter because there's a branch of physics that deals with what makes up protons and neutrons.
Mm-hmm.
And that branch of physics is called quantum chromodynamics. And it's abbreviated as QCD. So QCD deals with how quarks interact with each other. And one of the quarks is called the strange quark.
Ah, okay.
So that's where that comes from.
Gotcha.
I don't know exactly why, but the strange quark, for whatever reason, is important in that strange star or strange matter.
And I'm sure at some point I'll do more research into that, because I love those. I fucking love those Kyrgyzstan videos, man. They're just so informational,
I agree.
And they make them. It makes it fun to like watch too, the way that they do all the animations.
Yep.
Yeah. And I'm sure we'll learn more about that. So some little facts that I have here about neutron stars, and you can expand on any of these if you want. But so, you know, I put what I just said a minute ago. They're the densest thing in the universe. They're second only to black holes. And if they were any more dense, they would basically become black holes. Like, that's how unbelievably dense they are. And then kind of just like we were talking about with black holes, light bends around them pretty much just like a black hole. So like you can see light on the other side of the star, because it's just, I'm assuming because the gravity is so unbelievably strong within a neutron star that light bends around it.
Yeah. Now, I feel like your statement is correct, but I think it could be misleading.
Okay.
So just to be absolutely clarifying, I would like to say you can see effectively behind or underneath a neutron star when you're looking at it head on.
Yeah. And that's what I have in my head when I'm saying it. I probably just didn't do a good job of like explaining it. But
that's
we talked about
that's
it on black holes. It's pretty much the same thing.
Yeah.
So then something else I read was that their temperatures reach about 1 million degrees Celsius, where our star is only about 6,000 degrees Celsius. So not only are they unbelievably dense, they're crazy hot.
They are hot as shit.
Are they the hottest thing in the universe? Or...
See, I don't know galactic things in terms of temperature scale.
Mm-hmm.
But I would like to say, I feel like the closer you get to a black hole, the hotter it gets.
Yeah.
So I'm going to say no, they're not the hottest things in the universe. But I would like to add an asterisk to that statement because I don't actually know.
Gotcha. Okay. And then one of the other things that I had written down was basically the same thing, is that inside of it, they're actually pretty similar to planets. They have their own form of atmosphere, their own form of crust, all that stuff. Like, I thought that was pretty cool. Okay, so...
They have an ocean.
Really? What?
Yeah. Okay, so I'll explain that. So to go through this, we have to talk about neutron stars and what are known as binary star systems. This is specifically what I did my research on. Really?
Within
Yes.
binary stars? Yeah, I didn't go into too much depth on this. I kind of looked a little bit more at, I guess, pulsars. I kind of looked a little bit more at that, but yeah, go right ahead.
So a binary star system is a star with a neutron star. Well, in its most general, a binary star system is two stars orbiting each other.
Mm-hmm.
Specifically to neutron stars, there's one neutron star and one star that's similar to the mass of our sun in what is called a low mass X-ray binary system. So the star that orbits the neutron star, the sun-like star, loses material, loses stellar material, plasma, whatever you want to call it. And the neutron star takes that because of its immense gravitational pull.
Yeah, it looks like it's sucking from the star. There's like a line going from the star into the neutron star in models that I've seen. And yeah, it looks like it's literally fucking like sucking a star through a straw.
Yeah, that process is called accretion.
Yeah, that's pretty cool.
So when neutron stars take matter from their companion star, when they accrete matter, the matter becomes an ocean on top of the star.
That's cool. Okay, so like, is this similar to like a black hole's accretion disk? Because you said it's through like the process of accretion. So instead of it just completely orbiting a star, it kind of condenses on top into its own like ocean of matter, or...
Well, neutron stars and black holes both have accretion disks.
Oh, okay.
But the difference is the matter from the accretion disk on a neutron star gets deposited onto the star. Whereas in a black hole, it just gets swallowed into it.
It just gets sucked in.
Yeah.
Okay. That's pretty cool. I didn't know that. I read some interesting facts. I didn't realize that they had their own like form of ocean. That's pretty fucking cool.
Yeah, it's not like our ocean in very many senses.
In any sense.
Yeah.
It might have it has some molecules in it. That's about it. Okay, so I guess one of the things I wanted to talk about is kind of like pulsars, magnetars, things like that, because I actually never realized that a pulsar was a neutron star. I had heard of pulsars, obviously, like, you know, I've seen models of them, I've seen pictures of them, and they look dope as shit, but I never realized that it was actually like a neutron star. I thought it was its own like separate phenomenon. I thought that was really cool. I didn't know that. But so when a neutron star first collapses, they begin to spin insanely fast, like several times a second, and that's an understatement, because I've read that the fastest known spinning neutron star spins 700 times in 1 second.
Yes.
That is fucking nuts. So basically, while it spins, this kind of creates pulses because their magnetic field becomes so strong that it emits radio waves each time that it spins. And these are pretty much known as radio pulsars, which I think are the most common. I think I've seen there. I don't know how many there are in the universe, but they appear to be the most common, just like radio pulsars. And then, so this is kind of where I wanted to talk a little. I don't really know too much about magnetars. I know the magnetars are basically like neutron stars that their magnetic field is like a quadrillion times the amount that our magnetic field is here on Earth. It's literally like quadrillions of times. So maybe you can talk a little bit more about those.
Well, actually, I didn't do much research on magnetars. Like, all I know about them is that they are extreme magnetic objects. But pulsars, the reason we see the pulses from them is because it's almost like, imagine shining a extremely large flashlight throughout the solar system.
Okay.
Or throughout the universe, really, spinning in a circle. We are in the path of that flashlight. So once the flashlight crosses, I don't want to say crosses, but once it shines on us, we can see that as a pulse.
Yeah, okay.
So every time the star spins like 700 times a second, like we get 700 pulses a second. Once we cross into the, I'm just going to say beam for lack of a better word. Once the beam of waves from the star reaches us, we register that as a pulse.
Yeah.
And that happens so many times a second, depending on how fast the star is spinning.
Yeah. Yeah, that's pretty cool. Pulsars they're pretty interesting, but that kind of leads me into this one area that I specifically wanted to talk about, and I didn't really do too much onto this one, but I thought it was like really cool. So there's this pretty badass phenomenon that occurs when two neutron stars are orbiting one another, basically. And so apparently at a certain point, there's like this point where two neutron stars collide with one another. And it creates this own like separate type of supernova, which is pretty aptly named a kilonova, because they basically they destroy each other, they kill each other, and they slam in. And so I wanted to know how much you knew about that, if you've done any research into kilonovas at all.
So what I do know about kilonovas is that they are less powerful than supernovas.
Really?
Yeah, a kilonova is like the prefix to kilonova. Kilo is like kilogram. Kilo.
Yeah.
So it's not as strong as a supernova, but it is a burst that we can measure.
Yeah.
So when you have two large masses orbiting each other, like very large, like a neutron star, and they collapse, like they're going to not collapse, but merge, they are going to release a lot of energy.
Yeah.
And that energy is what you see in a kilonova.
I mean, that's pretty cool. I mean, nonetheless, I mean, the fact that two neutron stars orbit each other and fucking slam into each other and create their own form of a supernova, that's pretty badass.
Now, when two neutron stars orbit each other and eventually merge and create that kilonova, gravitational waves are actually formed as well.
Really?
Yes.
Okay. Does that have anything to do with the gravitational waves that we measured back in like, what was it, like 2013 or something like that?
2017, yes.
Oh, it was
exactly.
2017? Oh, shit, I thought it was even further back than that.
Yeah.
Really? Okay. So that's pretty much what we were measuring. We were measuring a kilonova, or
we were measuring I don't remember exactly what the event is, but we have measured black hole mergers, two black holes. Mm-hmm. We measured neutron star mergers, two neutron stars. And we measured a black hole and a neutron star merging.
Okay.
Through gravitational waves.
And can you describe, just like pretty layman's terms, like what a gravitational wave is? Because I did a little bit of reading on it, but I don't remember.
Yeah, so a gravitational wave is basically a ripple in space-time. Anything with gravity causes gravitational waves. Like you, Trevor, cause gravitational waves.
Yeah.
We just can't detect them because they're very, very small.
I am a small man.
Yes.
I am 5'7".
Now, neutron stars and black holes, specifically when they spiral towards each other and merge, like they produce enough gravitational waves that we can detect them.
Interesting. Okay. And that's got to be, I don't know, to me, that seems like a pretty, and obviously the universe is infinitely large, so when I say uncommon, I guess it doesn't really matter too much. But like, that seems like it would be a pretty rare thing for two, like, because a neutron star is a pretty extreme thing that occurs in the universe. So like, how likely is it that two neutron stars actually like orbit around you? Like there's two of them in a close vicinity. I feel like that would be a pretty rare event.
Within 1 billion light years from our planet, one of those mergers happen a month.
Holy shit! Are you serious?
That's the scientific estimate.
Oh my god!
Yes.
Okay, I mean, obviously, I don't know shit, but I don't know. It just to me, it seemed like a wow. Okay, like neutron stars are this pretty, you know, I don't want to say like uncommon thing, but pretty like extraordinary thing.
Yeah, like
and then like there's two next to each other, and they're just creating all these kilonovas. That's pretty cool.
Like they're relatively uncommon, but that's why within a billion light years,
Right,
like
yeah.
that's a very large distance.
I mean, still, like, fuck? That's a lot. Damn. Yeah. No. So that, I mean, like, that's all pretty cool. So, like, what happens then? And I'm sure the answer is that the black hole just overtakes it. But like, is there anything cool that happens when a neutron star pretty much collides with a black hole? Or
Well, I mean, the neutron star gets torn up by the black hole, and then the black hole just increases in mass because it swallows the neutron star.
And I figured that was like the obvious answer. But I mean, since their own gravity is so unbelievably strong. I mean, would that measure in any kind of like gravitational wave if a black hole overtook a neutron star? Or...
Oh yeah, like
okay.
The reason we know that neutron star and black hole mergers have happened is because we can see the gravitational waves. Like the gravitational waves have a signature, and you can tell what is being merged through the signature.
Just the fact that like there's a concept of a ripple in space-time and it's not like science fiction is pretty fucking cool. Like,
yeah, it's crazy to imagine, but to tell you what happens, this is slightly off topic, but ripples in space-time can be measured.
Yeah.
Like, have you heard of the LIGO and Virgo observatories?
Yes.
Okay, good. So, to give you a crash course for those of you who don't know, the LIGO observatory has 2 laser arms, which is like a laser beam shooting at a mirror that splits the beam. Like, these arms are 4 miles long.
Holy shit.
Yes. And if there is any difference in length between the 2 arms, it's registered.
Okay.
And the space-time ripples caused by black holes caused the 4-mile long laser arm to change length by, I think, 1/10 the diameter of a proton. But we can measure that. And because there is a difference in length, that's evidence for gravitational waves.
Yeah, you see that, like, that's insane that we have come so far in technology that we can measure things like this on like literally a microscopic scale. Like, that is insane. And like that's why the more research I've done into a lot of scientific concepts, the more it kind of baffles me when people who haven't done a whole lot of looking into it just look at stuff like that and they're like, what did all these scientists know? It's like a lot. They know a lot about how the universe works. Like a fucking shit. We are measuring things on a subatomic scale. Like we are that accurate. We have models that, are 90% accurate. If we keep running them over and over and over again, they keep producing the same outcome. If it walks like a duck, it's a fucking duck. Like, so that it's always funny, you see those like backwoods people like, scientists ain't no shit. They can't tell me if bananas are good for me or not. How do they know shit about space? It just like, bro, man, like we know a lot. And it's like for you to even think you can possibly wrap your head around it or just understand it from the outside and not doing a shitload of like devoting your life to basically doing this stuff is unbelievably arrogant. And that is a huge understatement.
Big facts.
Yeah. That's so read a book. read a book out there.
Or a few.
Yeah. No, just one. I'll be happy if you can just do one. Yeah. So, I mean, all of this stuff is pretty crazy, but from what I have like looked into it, one of the things that I never actually saw was from what I understand, neutron stars kind of die twice in their own way. They die from their original star state to become a neutron star, and then I guess they die again. But I actually don't know what happens at the end of a neutron star's life. Like, how does a neutron star finally go out? Because I didn't see much about that.
So that is actually very uneventful. A neutron star eventually just cools enough to become a relatively cold sphere in space.
So it just kind of becomes just like a dead planetary object.
Yeah, because I'm not sure if we can get too much into it, but there is a type of particle called a neutrino. Are you familiar with? You've
mentioned them a couple of times before.
Okay, so all you need to know is that neutrinos don't interact with a lot of matter. they can pass right through anything.
Okay, that's pretty cool.
So neutrinos that are formed inside the neutron star basically just fly through it from the core to the surface. And that reduces the neutron star's energy. So a bunch of neutrinos take the neutron star's energy, it decreases in temperature, and as a result, it gets colder. So enough of that happens over time to where the neutron star just gets, its temperature becomes eventually the temperature of the surrounding space. So it just gets cold, radiates all its energy away.
Damn. Okay. Yeah. I mean, you're right. That is a little uneventful, but I never knew. It never kind of explained because with a regular star, at some point it's going to become like a giant. Like there is some kind of process it goes through, but I didn't know it eventually just kind of faded out. So is it the same kind of story with white dwarfs? Then they just okay.
White dwarfs are just slightly less exciting.
They don't sound as cool as neutron stars. They sound like they're the lame version of neutron stars.
They're cool in their own way, but neutron stars are like the angry bigger brother.
Yeah, they're dope. Okay, interesting. So I think I've read, so obviously what I said earlier is that if neutron stars were any denser, they would become black holes. And I think I saw something, I can't remember, of like sometimes that happens, like they do become black holes. Do you know kind of the process through which that happens, like how that occurs?
Yeah, so typically what happens is if a neutron star isn't massive enough to become a black hole, then it needs to take matter from somewhere. Typically it takes matter from a donor star. So if it crosses the path of a unlucky star, or if it's in a binary star system, it takes matter from the star. And if it becomes dense enough, the neutron star collapses into a black hole.
Okay, that's so fucking cool. So yeah, so then that's where I was reading where it says sometimes they die twice, basically. So it's like you start off as a star, massive star, it dies, becomes a neutron star, and then it takes in more matter, it dies and becomes a black hole. Like,
yeah.
I mean, it's a pretty good chain of events. You were a star, a neutron star, and now you're a fucking black hole that just gets to chill there for trillions upon trillions of years. Like,
yeah, hell yeah.
If you're a star, you're immortal, basically. That's pretty fucking cool. So, so I don't know if you had any other like cool facts that you wanted to go into. I'm sure you probably do. But one of the last things that I have here in my notes and we heard it a little bit on that video. We watched a video before this of like what would happen if a neutron star popped up near the solar system. And as I'm sure you could probably guess, it just fucks everything up. But one of the things that they did mention pretty like in passing is that that scientists believe that if there was some type of life to exist on a neutron star, because the gravity is so strong, because it's so dense, that if life did exist on it, it would basically be two-dimensional. And I thought that was pretty cool. I didn't know if you had anything you wanted to add to that, or if you had read anything about that, but...
Yeah, unfortunately, I have nothing for that, because I think the prospect of life on neutron stars, as cool as it would be, I think it's very unrealistic.
I mean, it is horribly unlikely, but still, nonetheless, they were like, if it did find a way to like exist there, it would pretty much be flattened, because anything you put on it would just be flattened.
Yeah, so I guess if we're talking about putting things on a neutron star, mountains on neutron stars are at maximum only a few centimeters high. Like neutron stars are pretty much uniform because of their strong gravity. Okay,
that's pretty cool.
Yeah.
So and that video actually mentioned something else. Basically, kind of like when it has its own like star quake. So a little bit of what I read into. So like on Earth, tectonic plates slightly shift, and then you have earthquakes, volcanoes, things like that. But on a neutron star, if something like that was to happen, isn't it like pretty fucking insane? Like it releases an ungodly amount of energy or something like that.
Yeah. So there's a lot of energy held in the neutron star's crust, and that energy is because of the magnetic field. Like a neutron star has a very strong magnetic field. And the magnetic field realigns itself sometimes. Like it's the Earth has two poles, magnetic poles. And every magnet has these poles.
Yeah.
Sometimes on a neutron star, the magnetic poles realign. And when they do, because the magnetic field is so strong, it produces an enormous strain on the neutron star's crust and produces what is called a starquake. And like that video mentioned before, an enormous amount of energy is released in this starquake.
What was it? What was its like scale like of how crazy it was? Do you remember what it said?
It said like if a starquake happened within 10 light years and if the gamma ray burst hit us, we would be vaporized.
Oh, okay, there we go. That's how strong a starquake is. You know, earthquake is just like, fucking some people in California are fucked. But on a star, it's like, yeah, no, we will eradicate an entire planet.
Yeah.
So yeah, so I'm sure you have a couple of other things that you want to say about black holes, fucking neutron stars. So go right ahead if you have other cool things to add.
Well, at this point, it's all trivia, basically.
No, that's perfectly fine.
Just facts. So, I did some calculations before this podcast, and the gravitational strength of a neutron star is about 1 trillion times that of what it is here.
Okay.
So we have some number that represents how strong gravity is here.
Mm-hmm.
We call that G. A neutron star's G is 1 trillion times of what it is here. And to give you a little bit of perspective, an empty beer can on a neutron star would weigh 68 billion pounds.
Oh my God.
Now, a full can of beer on a neutron star would weigh 2 trillion pounds.
That is fucking insane.
Yes.
I want to know what happens to your body. Like someone just is like, yo, I wish that guy was on a neutron star. Like, you know, it was like a genie in the lamp or some shit. And you just pop like for 1 second on a neutron star. What the fuck happens to you?
That person is immediately deconstituted and he becomes part of the neutron star. Like, almost immediately that person is ripped into protons and neutrons. And like, that's it. He is the star.
The term ripped into the term ripped into protons and neutrons is fucking hilarious. Oh my God.
Like, assuming that you could survive on a neutron star, nothing in the universe would be able to pull you off because you would have to have an escape velocity of half the speed of light. Like, you'd have to move at half the speed of light to get off.
That's insane. Yeah. So yeah, if you were on it, I mean, it would take an ungodly amount of energy, something that we cannot replicate at all to get off of the fucking neutron star.
Like, nothing in the universe as it exists now would produce enough force to, one, rival that of a neutron star, but two, rival it so much to where that you're accelerated to half the speed of light. Like, it's physically impossible.
Yeah, that's insane. Well, I mean, just the fact of when the star collapses and becomes a neutron star, just the fact that the outer layers of the star move at 25% the speed of light to collapse into the star, like, just that alone is like mind-boggling.
Yeah.
Yeah, that's fucking nuts.
Now, another thing that I found interesting is, like, I was doing some more calculations, and if you put a neutron star with roughly the mass of a sun, how am I going to explain this? So there is a point where the force of a neutron star, the gravitational force of a neutron star, equals that of you standing on the surface of the Earth. Like, the Earth's force on you would be equal to the gravitational force of a neutron star.
Okay.
And the best way I could describe it in terms of distance is if you were standing on one side of the Earth,
mm-hmm.
and a neutron star was positioned exactly at the opposite side of the Earth,
mm-hmm.
the force from the Earth and the neutron star would be equal in terms of, like, magnitude.
Okay.
So imagine then if you put a neutron star about an Earth's distance away from where you're standing.
Okay.
The forces would be the same.
Okay, gotcha.
If you move the neutron star closer than an Earth's distance, then the neutron star would begin to win out.
Okay.
It would actually pull you and everything on the planet towards it. No, I think the coolest thing was, like, if there was a neutron star, say, a mile above the Earth, just about everything on the Earth would be attracted to it.
Yeah.
I mean, that's just it. I think that's awesome.
I mean, yeah, and it also, I mean, it sounds right. I mean, it just pretty much sucks everything in, and then, as you said, you become one with the neutron star.
Yeah, like, I didn't do any calculations on when you would vaporize, so my calculations assume that you would survive to experience all of this, but I don't think that's realistic.
No, yeah, not at all. I mean, I still can't get over you phase onto a neutron star and you're ripped into subatomic particles immediately.
Yeah, like you would not survive.
Yeah, no, we've talked about Superman punching you, right? Yeah, that's pretty much that.
Yep.
You just turn into liquid plasma immediately.
This might be interesting. This may not be interesting to some people, but since neutron stars spin so fast, if you were just standing on the surface of a neutron star as it was spinning, your speed would be measured at about a fourth the speed of light.
Holy shit.
Yeah.
So, okay, realistically, a neutron star is like Earth. You can survive on it. It's, habitable, and you're just standing on it while it's spinning that fast. Do you just get ripped apart?
I mean, I guess it depends, because if we're assuming that you can survive on it, then we're also assuming that you've adapted to the insane speed.
Okay, you adapt to everything but the insane speed. Like, it has an atmosphere, you can breathe, like all that shit. Like, but you have not adapted to the speed. You just pop up on it. Yeah, are you like torn apart?
You would be torn apart.
God damn it. Everything fucking kills you on this thing.
Well, I mean, imagine... Oh my God. Like, could you imagine standing in a place and then a different part of your body, like say at your hips, one part of your body begins to move at like 300 miles an hour?
No.
Okay, exactly.
Well, because you'd be ripped apart.
Yes, exactly. Which is why it's even worse moving at a fourth the speed of light.
Yeah.
Like, your body would just not be able to handle the sudden acceleration that you would experience, so you would be ripped apart.
Your bottom half would be moving like way faster than you, right? Or
your entire body would not be able to handle it. Like, you would just become a soup.
Damn it. Everything in the universe wants to kill us.
Yeah. Everything extreme in the universe wants to kill us.
Yeah.
Neutron stars are just so interesting, dude. They're so cool.
Yeah, no, yeah. Like I said, they were definitely one of the strangest things that I had read about. Just kind of like, when you get into their basic elements, how they make up structures, kind of like a planet, like the pasta aspects of them, what happens within, what might be so strange that we have to literally call it like strange matter. Like they're very interesting. They're very unique. And I thought they were really fucking cool. But all right, yeah. I mean, if that's all that we both have, I want to thank you guys so much for tuning in to another episode of the Modern Goonies podcast. We will be back next week for season 1, episode 10, which will be our last episode in the season. And we want to thank you guys so much for tuning in so far. And we hope that you liked the last episode. And I've been your host, Trevor King Minor. And this has been my badass co-host, Michael Ross.
Live fast, eat ass.
Live fast, eat ass. And good night, everyone.